Hi, my name is Ashley Blue. I work at Artifactual Systems as a preservation specialist and systems archivist.
Hello, I'm Libby Hopfauf. I'm the program manager and audiovisual archivist for Moving Image Preservation of Puget Sound, or MIPOPS, and I'm also the audiovisual archivist for Seattle Municipal Archives.
Hi, my name is Andrew Weaver, and I work for the University of Washington Libraries as the Media Preservation Librarian.
And I'm Dave Rice. I'm the co-chair of the AMIA Open Source Committee.
Hello everyone, thank you for tuning in today for a DVRescue project update. Before we begin, I'm going to present a brief overview of DV videotape formats, their historical value, and significance in our field. DV tape refers to a family of digital videotape formats, including mini-DV, HDV, DV-Cam, and DVC Pro, commonly used from 1995 through the 2010s. The affordability and compact size of DV tape enabled many cultural, journalistic, and humanities organizations to create unique audiovisual documentation for the first time. These formats were not commonly used for media distribution. Thus, a collected DV tape is very likely a camera original, or a unique recording rather than a copy. DV tape is far more susceptible to contamination, damage, decay, and environmental factors than any other videotape format from the same time period. At the peak of its era, DV was well supported by multiple software applications, such as Live Capture Plus, DV Grab, and Final Cut Pro 7. However, now nearly every application supporting the transfer of DV is unsupported. Websites are offline, aged applications are difficult to access, and such applications do not or cannot run natively on modern computers. Premiere Pro and QuickTime can both digitize DV still, however, they do not capture the raw DV stream. In 2018, MIPOPS and RescuePaids received a research and development grant from the National Endowment for the Humanities to fund the collaborative project DVRescue. The project is working to develop procedures and tools that support migrating data from DV tapes into digital files suitable for long-term preservation. As we have laid out, this will fill an urgent need for DV tape transfer tools that can rescue content from at-risk digital videotape formats. The DVRescue project will entail 2 years of work, which started in May 2019 and was originally set to conclude in April 2021, but due to COVID-19 restrictions, it will now run until October 2021. During this time, we have been and will continue working to develop open source and freely available software, user research and testing, and create documentation to help define and perform comprehensive, automated, and easy-to-use data migration techniques. As part of the collaborative effort, MIPOPS and RescuePaids selected and invited a group of participating institutions currently collecting DV videotape to allow us to conduct research, define preservation workflows, establish standards, and develop the most impactful tools for capturing content from DV videotape. Our participating institutions include the groups represented on this slide. At the beginning of the project, we took an initial survey of our participants to gather data to aid the development process based on the sample group's specific needs. In order to determine which groups can test components related to specific formats, we gathered information regarding DV formats they had in their collections and which of these they were able to transfer with decks they currently owned in-house. To ensure that DVRescue would be compatible with the workflows of our test group, we also inquired what types of operating systems they were using along with which capturing softwares. To ensure we were able to effectively instruct users on how to use the tools and provide a variety of resources, we wanted to make sure we accommodated all learning styles and skill levels. This is the MIPOP standard, but we consistently poll users to ensure we are addressing their needs. The components of the DVRescue project plan include DV guidance, DV analysis, DV packager, DV capture, DVPlay, and DV merge. Each of these will be discussed in detail throughout this presentation. As I mentioned, one of the components of DVRescue is to develop and pilot universal training materials and tools for ready deployment using a selection of partnering institutions as a test group. In order to provide accessible training and guidance to the archival community, we are working to create documentation that addresses all learning styles and skill levels. DV guidance will comprise a sort of encyclopedia for all facets of DV videotape preservation. The documentation will be available in both on and offline formats. We'll provide video, audio, textual, and visual examples and instructions to address the following topics: background and history of DV, DV formats guide, training videos and documentation, transfer station setup instructions, shopping lists, deck guides, file care or post-capture best practices, capturing best practices, artifacts, identification and solutions, glossary, and additional resources. In order to empower organizations not currently digitizing in-house to set up DV workstations or to assist with the workflow improvement and maintenance for those who are, we are compiling resources to make the process simple, cheap, and easy. These are some examples of shopping lists we'll recommend for cleaning and repairs. They are currently available online, and this is an example of the PDF offline format. While all of these sections will be updated as needed to accommodate changes and reflect improvements and modifications, some of them, if not all, will be contribution-based living documents such as this deck guide. As much as it is my dream to have every deck ever manufactured, MePops lives in a tiny room that is shared with an office-wide copier, so that might be unrealistic. This will be a fantastic collaboration opportunity similar to AV Artifact Atlas to have people add to this list with additional decks accompanied with their experiences and the specifics of them. We will be providing setup instructions and transfer recommendations for all operating systems, including Mac, Linux, and Windows. These instructions will include specific details for all possible configurations, cords, and adapters needed for all deck outputs and available parts on multiple generations of computers.
Within the DVRescue project, when we're handling the process of transferring data from a tape to a file, we're using different tools depending on what platform we're on. If it's Windows or Linux or Mac, it's kind of a different tool that's handling all that communication and transfer of data into a DV file. But once we have that DV file, it's FFmpeg that's doing a lot of the heavy lifting from there to handle playback, analysis, rewrapping it into a container. Like it is for a lot of open source audiovisual projects, FFmpeg is just playing a substantial foundational role that we're building upon. So in diving into this project, we kind of have to address some of the outstanding issues that exist in FFmpeg as it relates to reading DV as it comes from tape. So in this part of the presentation, I just kind of want to highlight like one of those development stories as it relates to a particular type of audio error and situations where DV processed through FFmpeg could result in a file that loses audiovisual sync. So to understand this issue, we need to consider the structure of DV frames in a DV file. So a DV frame is, I think it's a lot like a film frame, where each frame is like the same size, and it's also like a self-contained unit that has multiple pieces of information in one thing. So a DV frame will have video, audio, metadata, like all structured together in one thing. Whereas in a lot of audiovisual formats, like a lot of container formats, audio and video are stored separately. But in DV, they're all kind of stuck together. DV isn't really just a video codec or audio codec. It's this compound codec of all types of information, all structured together into one block of data for a frame. So some DV players, when they reach like an unrecorded gap in the tape or it's put into stop mode, the DV player will create a frame that has like a still image of like a prior frame. It's just like a frame with no unique information. It's just a copy of what it's seen recently. So you end up with a frame that has this video information, but then in the audio section where the audio data would normally be, it's all filled with error code. But then also it doesn't have any metadata to contextualize it. So there's no sampling rate or channel count. Every aspect of the audio section is just blank, as if it's a frame that has this video to show, this just kind of like synthetic copy of a prior video, and then there's the audio is just all emptied out. So when FFmpeg is reading, it's getting all these DV frames that have audio and video together, and it's taking them out separately and saying, here's audio data coming out and here's video data coming out, but then it hits a DV frame where this instance occurs. Then it's able to output the video, but then there's no audio to share. So no audio comes out, no silence, nothing, because there's no context for any audio to come out. But then if in subsequent frames, there is, again, audio and video, then FFmpeg starts decoding that audio and video from those frames and outputting it. But the result is then you have audio and video coming out at different rates and different amounts. And like when those gaps happen, you start to lose sync between the audio and the video. There were a number of different like kind of ways to solve this, but one thing we realized is that in FFmpeg, all the audio and video data has timestamps so that that audio visual information is attached to a timeline at a certain point. And those timestamps for the audio data were incorrect when this issue would happen. So one of the fixes that's in the development listserv right now for FFmpeg is to affix that timestamp to all the audio packets of data more accurately, so that the video and audio, even if they're not there, they're all precisely timed and aligned to on a timestamp. So with that fix, then you get audio and video coming out, and then instead of losing sync, you just have gaps in the track. So that's the solution we're using in DV Packager presently, so that you get out the same duration of video frames and audio frames together. So, I mean, this is like one area of the project, like where, because we're building on open source tools, we have to like fix issues in those tools and not just within our own project. So by like working on addressing the challenges of DV within DVRescue, like some of the solutions and the efforts are having this side effect of like fixing DV and all these other projects that rely on these open source foundations too.
While a lot of DVRescue's early research was focused on the challenge of getting DV capture working on Apple computers via Mac's audiovisual framework, AV Foundation, DVRescue is a cross-platform project that aims to support workstations on Mac, Linux, and Windows. Accordingly, after initial successes on the Mac side, we have undertaken research and development on how to seamlessly replicate DVRescue's functions on alternate platforms. Similarly to how early Mac-side research focused on FFmpeg control of AV Foundation for Macs, the Linux side of research for DV capture has focused on the FFmpeg device IEC 61883. IEC 61883 being both a mouthful and a technical standard used for the interface of FireWire equipment. This device requires certain libraries to be installed through the standard package manager, example commands for Ubuntu shown on slide, and then FFmpeg must be compiled with a flag enabling the device. Once this is done, however, no further actions were necessary on the system to get things working. Capture of DV tape via FFmpeg is simple and effective. Device control has also been facilitated through the Linux command line tool dvcont that allows control of DV devices. On the Windows side of things, we have also been testing the application of other devices available through FFmpeg. In this case, the DShow device that taps into the DirectShow multimedia framework used in Windows. This also requires an installation of drivers. A third-party resource with instructions for this is linked in the slides. But after drivers are installed, capture is seamless. We haven't yet found a suitable and open device control tool to enable DEC control beyond capture, but this is supported by DirectShow, so investigations have begun on a custom solution. We wanted to highlight our non-Mac testing station, as it not only has proven very effective for advancing DVRescue work, but it also stands as an example of a low-budget capture station and of how affordable non-Mac DV stations can be. It consists of one of the cheapest refurbished Dells available for purchase on Amazon and a $20 DV capture expansion card. This is dual booted with both Linux and Windows, with the Linux install being free, and provides all the capabilities needed for both DV and digital preservation. Key takeaways of this work have been that the underlying frameworks on the respective systems still work very well with DV devices, and essential drivers are still readily available. This was obviously good news for the DVRescue project. Another key takeaway is that dongle chains seem to be problematic for Linux. While daisy chaining Thunderbolt adapters on the Mac side of things has presented no problems, it has caused issues on Linux. This is a problem for laptops, but can be fixed due to the ability to install expansion cards on desktops. Happily, expansion cards are also much more affordable than Thunderbolt adapters. And lastly, effective DV capture stations don't need to break the bank. Both these underlying resources and the eventual DVRescue tool are cross-platform, which can help to avoid the higher upfront costs of Apple devices and computers while still enabling fully functional DV preservation.
Central to DVRescue is how we document what is happening inside a DV stream. So we've developed an XML format that is responsive to the specifications and the realities of DV. As we want to make software and workflows that are easy to use, we expect that often this XML document is going to be rather behind the scenes. But what information we gather and store certainly impacts the possibilities and opportunities of what we can do. So we want to show you this XML format directly. As the DVRescue command line tool analyzes the DV stream, this is the XML document that it makes, and it tracks things like the technical properties, information about frame coherency, and a condition assessment. So technical properties include the basics like frame size, aspect ratio, frame rate, chroma subsampling, audio channel count, audio sampling rate, and a few others. Often these characteristics are going to be consistent from frame to frame across an entire tape. However, they can change. Like someone using a camcorder could switch from 4:3 to 16:9 in the middle of a tape, or from a 2-channel recording to a 4-channel recording. So those particular events and technical properties we need to track, not just for the beginning of the frame, but for the entire recording. In regards to coherency, we also want to track where a DV recording can break from the common expected pattern. So we track information about its coherency from one frame to the next. This information includes things like gaps in the time code, jumps in the recording timestamp, like you set your clock in your camcorder and you record. So if you stop recording and start a new one, you'd have a jump in time. So we track those kinds of gaps. We also track if that kind of information is repeated rather than incremental, which would be unexpected. Then we track, like if we're making a transition from like video with captions to no captions or vice versa, or changes in technical properties, as I mentioned. This information that we gather is really helpful later when we're setting up chapter tracks in a repackaged file, or we're like deciding if we want to take a DV file and split it according to certain occurrences, like a recording flag or a timecode jump. Getting back to like one of the sort of more essential pieces of data we track is a condition assessment. So this means the DVRescue command line tool is like reading every frame, and every frame is divided into blocks. As those blocks are transferred from the tape to a file, the tape is containing checksums for each block. So the video deck reading each block is able to verify if the block is correct or not, pass or fail, and make notes in the DV stream on if it was a problem or if it's okay. So we track all these notes, and we track the location of them and the occurrence rate. We track this pretty granularly because we found that by tracking the location of where the errors are happening within the frame, we can sort of inform and diagnose what is wrong with the transfer. For instance, like if you open up a DV video deck, like there'll be that little drum that like spins around the tape, and there's 2 sets of readers on either side of it. One is reading even numbered diff sequences of a frame, and one is reading odd numbered diff sequences of a frame. So if the error rate between those 2 readers has a disparity, like all the errors are just on the odd numbered diff sequences and the even ones are fine, it can kind of help inform us that it's not necessarily that the tape is scratched or crinkled or damaged. It's that the video reader itself is obstructed with like dirt or dust or something, and that a cleaning could help improve it. This XML shows an example where all the errors, and this is noting video error concealment and audio errors, are happening on even numbered diff sequences. A retransfer of this tape was able to improve the issue. So with the DVRescue command line tool, all this information is stored in this XML file, and we use this information to package DV, graph errors, visualize problems. This information is kind of essential for all the subsequent actions in the DVRescue suite of tools that we're developing. So that's my XML tour. One component of the DVRescue project is DVPackager, which is currently available as a command line tool. That takes a DV stream, which is a file of a DV extension, and packages it into a container format such as QuickTime or Matroska. As an overview, in the DVRescue project, tools and guidance we're designing recommend capturing DV from a tape to a file as a DV stream, then analyzing it and packaging it into a container. So a tape to a DV file, then to a container like QuickTime or Matroska. There have been some tools like Final Cut 7 and Adobe Premiere that skip that intermediate step and try to capture directly into a QuickTime file. But we find that there's a lot of disadvantages to this approach. For instance, DV tapes can contain changes in aspect ratio, audio channel count, timecode jumps, and other information that isn't easy to accommodate into a singular QuickTime file. If Final Cut is capturing a DV tape that's 4:3 and 2 channels, and then it switches to 16:9 and 4 channels, typically a software is going to stop the transfer and just stop, not like make a new file. So trying to capture DV can often be a rather tedious approach when dealing with incoherencies in the DV stream. The approach that we're taking is all about getting all the data off the tape as is into a temporary DV stream, and then designing tools to sort it out later by doing all the analysis, separating out segments by their properties, and repackaging them according to selected strategies. So one could consider storing a DV stream as it is, with its DV file extension, as would be done with some tools like dvgrab and AVHScap. However, there's also interoperability challenges with this approach as well. Maybe players for DV files will determine the frame size, frame rate, and sampling rate by looking at the first frame, and like when those changes in the middle, playback problems can occur. Additionally, since DV from some tapes might not be in the most valid form, relying on the first frame to discover and clarify all those properties can lead to inconsistent results. So by doing a more comprehensive analysis and then strategically rewrapping the data into a container that's more common, like QuickTime or Matroska, that asserts all these technical details, we can help improve the interoperability and stability of DV frames by moving them into these more commonly supported containers. As noted before, DV is a complex stream where each frame contains not only audio and video data, but timecode, captions, camera metadata, and information about the transfer itself, like how successful it was as far as moving the data accurately. Since DV is used particularly as a camcorder format, information like the metadata inside the files can include markers to say where the record button was pressed, the time of the clock, the camera settings like white balance, autofocus settings. So when a DV videotape player is unable to properly read portions of the frame, it also makes transfer notes as far as what type of error or concealment was included. So getting back to our tool called DVPackager, it needs to do a few things. It has to evaluate the DV frames to determine their characteristics and any significant changes that happen within them. It has to repackage the audio and the video from those DV frames into a common container format. And then it has to also consider other non-audiovisual details like captions, camera metadata, recording markers, and make that data accessible as well. Although DV is rich with metadata, it can often be very difficult to access, use, or benefit from the data within it. Like when cataloging DV content, it would be really helpful to know the date of this shot, or to know that this shot was 2 days after the previous one. Or to use camera metadata to relate many tapes that were all shot together in the same weekend or the same event, even though those tapes might now be distributed in your collection. In order to make this information accessible, we've been using chapters and subtitles. So with DVPackager, when there's a timecode break or a discontinuous jump in the recording timestamp, or a flag to note that the record button was hit, we can set that as a chapter in the resulting file. This aids substantially in the navigability and a review of DV content, so you can clearly see where all the shots are of it, and it can all be broke down into its components by using that metadata. So this makes it DV a bit more emulating the type of menu structure you'd have in a DVD, where you can easily jump around the timeline according to markers. So as DV frames can also contain captions, we've developed a way to extract that from the frame headers, convert it into a subtitle format, and embed that into a QuickTime or Matroska container. So this example shows a demonstration file of DV caption abilities by taking a DV caption demo file and running it for DVPackager to produce this pop-on subtitle track. So then there's another piece of metadata, which is embedded timecode, clock data, error information. And we've been trying to figure out how to make this information accessible too, so that you can easily review the content. So we've been testing using subtitle tracks to make this information accessible. Generally, subtitles are intended to provide an alternate method to make the audio tracks accessible. Whereas here we're bending the rules and intentions a bit to use subtitles to make the technical metadata accessible. So many common video players that we're using, such as VLC, MPV, and QuickTime Player X, they don't support showing embedded DV timecode or camera metadata with their interface. However, by gathering that metadata and using it to construct a subtitle track and then embedding that into a rewrapped file, we can then take advantage of much more widespread subtitle report to make this technical information available. So this video is a demo of the current state of DVPackager. It's able to take all this camera metadata, recording metadata, and make chapters and subtitles so that all the information inside a DV file is then much more accessible and easy to use with accessible players. So DV Packager is currently in our installer as a command line tool, and we look forward to porting it into a GUI in the upcoming months.
DVRescue development has gone hand in hand with vRecord development, so we wanted to give a quick overview and rundown of that process and where capabilities stand. Quickly, for those who aren't familiar with vRecord, it is a cross-platform archival capture tool created and maintained by members of your very own AMIA open source committee. It supports capture of both video and audio sources, and now thanks to DVRescue, also DV. It helps with calibration and capture, both by supporting a large range of digital scopes, as well as direct capture to formats such as FFV1 Matroska. As the process of DVRescue development has been purposefully iterative, integration and testing through the existing vRecord tool has been incredibly beneficial for both projects. As underlying capture methods for DVRescue are tested and developed, they have been rapidly integrated within vRecord, which aids in the gathering of feedback from our project partners through applied use. This has proven invaluable for discovering problem areas in capture in advance of our final deliverables. This also has been great for the vRecord project, as it has expanded its utility into the realm of digital video. This means that vRecord users, if they want, will be able to continue to use it as a one-stop shop for AV capture. Current integration of DVRescue in vRecord uses FFmpeg devices and the AVF control device that are underlying DVRescue work. It allows monitoring of video and audio during capture and creates a DV file with logs. It now also is integrating functionality from the DV Packager tool in DVRescue that adds capabilities for things like automatic splitting of files using recording metadata and the repackaging of these outputs in expanded formats.
DVPlay is a command line tool component of DVRescue. It is a quality control tool utilizing a player to support reviewing and inspecting the resulting data of a DV tape to file transfer in order to highlight errors and concealment that may have occurred either as a result of tape damage, issues with the tape deck, issues with the transfer, or camcorder recording errors, and aid in deciphering between them. This is an example of a training video we created for DVPlay. To use DVPlay, simply open the terminal and type in DVPlay, and then drag in the file. Then FFplay will open a window displaying a frame-by-frame grid playback. So you'll notice that there's just video running through, frame by frame, and nothing is highlighted in yellow. That means that this is a perfect capture. This test tape was recorded at MePops using a feedback loop between a DVC Pro camcorder and a tube TV, created by MePops communication manager Paul Siple. If you type in DVPlay-X and drag in the file, then you'll notice that a folder is created with an XML file in it, but there were no JPEGs added. That means that this is indeed a perfect capture. If you type in DVPlay-M and drag in the file, everything that is highlighted in yellow has no errors. So it's the opposite of regular DVPlay. But let's try a problematic file. For reference, this is a tape that I purposefully scratched to see how scratches would present in DVPlay, so that we could create documentation and detect them. As you can see, there are lots and lots and lots of JPEGs that are being created through DVPlay-X, and that is because there are a lot of errors because of the scratch. So let's run it through DVPlay and see what that looks like. What type of errors will it highlight? And as you can see here, all those yellow lines that are running through at the beginning, that was the scratch. So if you look at the JPEGs, each JPEG is a frame that contains an error, and highlighted in yellow is where there is missing or problematic information. In this case, the information is missing because there was a scratch, and there were lots of frames that it scratched. And then if we open the file in QuickTime, we can see that all those blocks right there are signaling that information was missing, and the error concealment tried to fill in that missing information by copying frames that came prior to or after the frame that's missing the information. But since a bunch of them were missing information, it became very blocky and chunky. Part of this project will be to contribute DV artifacts to AV Artifact Atlas. Due to COVID-19 restrictions, we've had to make some adjustments to the DVRescue project. Seattle City Hall, where the MePops office is located, has been closed to the public since March and will continue to be closed until at least the end of the year. We've migrated training and workshops to gather feedback to a virtual setting. Luckily, I had the opportunity to bring home the equipment needed to assemble an at-home DV transfer station. This has enabled us to continue researching and documenting DV artifacts through rigorous testing. As we continue to develop this documentation, examples, methods of identification, and possible solutions will be contributed to AV Artifact Atlas. We will follow the platform standards of describing what each artifact looks like, possible causes, if it can be fixed, and if so, how. Each artifact will be accompanied by image and video examples, as well as how to use DVRescue tools to identify and resolve the error. Using the example that I presented during the DVPlay demonstration, a scratch can be identified prior to playback during tape inspection by flipping open the cassette door to check for damage. However, if the scratch was created at a different segment, it may be deeper inside the pack and unable to be detected upon visual inspection. How do you check to rule out that the artifact is not possibly a dropout or a head clog? You can run it through DVPlay, and like I demonstrated earlier, these vertical lines running through the image are a very reliable source indicating a scratch. Another way to check is to look at the JPEGs generated by DVPlayX and compare them with the same frames in your preferred player. And as you can see here, even without running through DVPlay, these error frames came one right after the other, and there's a line that goes down indicating a scratch.
If you have a mini DV that is somehow perfect and the perfect, cleanest DV tape player, then if you put that tape into the player, read it into a computer, and then rewind the tape and read it into a computer again and take those two files. If everything is perfect, unrealistically perfect, then those two files should play the same and sound the same. They should basically be two digital copies of the same source. But mini DV tapes will very rarely be perfect transfers. Mini DV tapes are made to be cheap and small, and regardless of how cool and dry your archive is, these tapes are probably going to include audio dropouts, video or concealments as you transfer them. So one of the kind of experimental areas of the project that we've been working on is being able to take multiple transfers of the same tape and consolidate the best parts of multiple imperfect transfers into a slightly more perfect transfer. So I'm going to delve into this, some of our experimental data a bit here to show you what's kind of in the works. So first I'll approach this by looking at timecode breaks. So these two graphs show two transfers of the same 1800 frames of a DV tape, and they have different gaps in like timecode jumps and recording timestamp jumps at different places. And this is because the way these two transfers were made was on a computer that was dropping frames, wasn't able to keep up with the transfer. But you'll notice on the graph that where those drop frames are on the timeline don't line up. So by taking these two files and putting them as inputs into our DVRescue command line tool, we can then iterate across all the frames, figure out their time code, figure out how these two streams align, and for each frame we can figure out if the time code is valid and readable, or sometimes we have a frame but the time code isn't trustworthy, like the time code information is missing or broken itself. And we can figure out if a frame is missing, if a frame is present in one but dropped in the other. So this column kind of is showing how we're like lining up and recovering from a dropped frame, a frame that's not present in one stream but is in the other. With this command line tool, we can then take these two inputs and merge them back together. So we make one output file that has all of the frames that are on the tape, whereas the two files we started from both had missing pieces. So to take this approach and move it up a level, we can then start to compare things on the block level and compare the quality between the frames of multiple transfers. So this example right here shows a portion of glitchy tape which had 6 transfers done on it. So all 6 of these input streams can be inputs into DVRescue, reads through all the 6 copies. If one of those copies has a perfect frame, like all the blocks are valid, then that is used and sent to the output file. If it's not perfect, it goes to the next of the inputs, sees if the time codes align, if everything matches up. So in most cases, it's picking like one whole frame from a transfer if it's able to find a perfect frame. But in this example, you can see like frame 740, like there's tape damage on the tape significant enough that none of the 6 transfers over that frame were able to get all 1500 blocks of the data out correctly. So you can see like the summary line on the right here says that this frame was assembled using blocks from all 5 of the copies, all 6 of the copies. The last one, it was using 1,475 blocks. And then from the others, it was contributing 23 blocks, 1 and 1, and then 2 of the copies like didn't have any blocks to add on to that. So from going from a very glitchy frame, we can then get to a quite complete frame. It just still has 19 bad blocks coming out of it, which is a little bit more than 1% of the frame is glitched, whereas before a lot of it was. Currently in our command line tool, we can combine multiple DV streams into a better stream by like merging them together according to like where the best quality is. But we imagine like integrating this into our capture utility soon as well. So that way, if you're reading off a tape into a file, well, you would be reading off a tape into like this DVRescue buffer that would be determining the health of those frames. If the frames are okay, they would be sent out to a file. If they're not okay, it would do some evaluation to figure out if it's bad enough to stop the transfer, rewind the deck, try to do a second pass over it to see if it can get a better frame, and then either mix those 2 frames together or prefer one frame over the other and like send the best frame out to the file that's happening. Live Capture Plus used to do something similar in its transfers. If it was able to find certain encounters of error frames, it would back up the deck and do a retransfer. So we're trying to take this approach as well, so that if we do have errors when we're reading off of a tape, we can have our software like do a double take, rewind, take another look, and try to make the best copy out that it's able to do so. At the end of these DV merging summaries, it kind of tells you how much of, like how healthy each capture was. So you can see here for all the input files, what percentage of the frames are healthy. This would be like frames that are perfect, where every block is valid. And then it shows you for all the blocks, like what percentage is valid. And then the next part of the summary is like how it's getting merged. So it's telling you like what percentage it's using of each file in making a merged output together. And then what the percentage of health is at the end, and what the how much of an improvement that was over the best file. So we can see here the best file is, what is it? It's like 98.6% of the frames are healthy, and in the end result we have 100% of the frames healthy because we were able to use all of the inputs to combine and make one very accurate one. In this example, we just got like really lucky that eventually with enough passes we were able to get valid reads off every block of that section of data.
DVRescue will include a collection of command line tools to perform a variety of tasks with DV from tapes. But for many users, digitizing DV tape might be their first foray into videotape digitization. With the right guidance, we think that building a DV transfer station could be a much simpler ordeal than a traditional analog videotape transfer station, so we wanted to have DVRescue provide an accessible interface to users new to videotape preservation. Much of the development work for the DVRescue project has been from the ground up, solving one challenge at a time, such as deck control, transferring data from tapes on various operating systems, packaging DV into the formats that archives prefer, and providing analysis of the transfer. As these underlying functions have progressed as command line tools, we started to assemble them into a graphical user interface to make it easy for the users that this project aspires to serve. The GUI is very much a work in process, which we hope to share for testing and review later this year, but here are a few drafts we are working on in the meantime. The drafts of the GUI delineate major functions developed in this project, with an initial focus on transferring DV from tape. The major functions are transfer, analysis, package, and playback. The GUI will also include a player particular to the issues of DV, where error concealment can be reviewed and inspected closely to provide a user with visual assurance of the quality of the transfer. The analysis interface will itemize out the segments of the DV transfer to note where events happen, such as a jump in the record's timestamp, an audio dropout, or video error concealment. And the packaging interface will allow users to determine what and how to save the transferred DV stream into a preservation-ready file. Right now, though, we are really focused on transfer. This interface shows one mini interface for each deck attached so that the user could transfer DV from 1 to 6 video players simultaneously, with each deck being able to be controlled and monitored independently. Alternatively, if you only have one transfer, they will only see one on the screen. And as Andrew alluded to behind the scenes, this interface will use different tools for control and capture depending on the operating system, but those various tools are all mapped to the same buttons in the interface, making it as easy as possible for users that want to get started with digitization. Now's the part of the presentation where we want to hear from you. No, don't yell at your computer screen, just pop on over to some of these URLs. From the main MePops page, you should be able to get to our blog, our codebase, and get the latest information about this project. For feedback, we highly encourage you to send an issue to our issues tracker on GitHub. From this page, you can check out a link to our daily builds. It's in the far right corner under About. Here you can download the latest and keep track of our progress as we address development work, improve the GUI, and help fix the bugs and add the features that you ask for in our issues tracker. If you're uncomfortable using GitHub, just email us. We also have a great documentation page where you can see our progress. This project is intended to provide context to not just how DVRescue, the software application, works, but a holistic approach to comprehensively managing your DV collections, from initial assessment, understanding of the formats, how to set up a transfer station, how to prepare tapes for capture, and all the tools you need to manage these physical objects. And after using DVRescue, it will provide guidance for file care, helping with artifacts and potential resolution, and additional resources to help you perform solid digital preservation work.